Hello, this is the start of chapter 8, which is mechanical properties of metals. In this chapter we talk about what are stress and strain and how they are used instead of load and displacement or deformation. We'll talk about what is elastic behavior and what materials deform least and when materials deform elastically. We will also talk about plastic behavior and at what point does permanent deformation occur, what materials are most resistant to permanent deformation or plastic deformation, and we also talk about what are toughness and ductility and how we can measure these parameters. Assume a bar which is fixed at one end and deforming the other end. Of course, if we look at the small part of the bar, we see groups of atoms that are attached to each other and there is a bond between them. If the load is applied, then we see displacement in the end part, or we see elongation in the bar, and this is due to the stretch of the bonds. And if we remove the load, you will see that material or the bar returns to its original or initial stage, and this is because atoms returns to their initial position. This kind of deformation is called elastic deformation, and it means reversible. So what's happening here, the load, by increasing the load we have increasing the displacement, and when the load is decreased, then we have decrease in the displacement along the same line until we reach to zero value. The elastic behavior is not always linear. We have non-linear elastic behavior as an example in polymers. If the deformation continues, what's happening after atoms are stretched, then we will have plane shear, which is shear along the planes that we have a more number of atoms or the planes or directions that are highly packed. So what's happening here, we have some displacement which is due to the expansion of bonds and some displacement due to plane shear. If the load is released, the part which is related to the enhancement or expansion of the bonds will be recovered, but the part which is due to the shear or planes shear will be permanent and it won't be recovered, so we will have a permanent displacement. This is shown in metals force displacement curve. As you see here, we have linear elastic part here, and after that we have a non-linear part due to the plane shear. And when the load is removed, the part that is related to elastic displacement, this part will be recovered. The part that is not recovered is called the plastic or permanent displacement. So plastic displacement means a permanent displacement. So if the load is applied normal to the same bar, and we look at the chunk of that bar, and we divide this normal load or normal tensile load divided by the cross-sectional area, which is normal to this load direction, then we can find tensile stress as defined here. The unit is Newton per meter square. Meter square is coming from area and Newton coming from force. If the load is not normal and has an angle with this plane, then we can resolve it into tensile force and shear force. Tensile force divided by the area will give us normal force or normal stress or normal tensile stress, and the shear force divided by the area will provide the shear stress as defined in this relation. Bear in mind that A0 is the original cross-sectional area before loading. Of course, this value will change after loading a little bit. One of the common states of stress is simple tension. Assume this drive shaft mechanism. This shaft is rotating and it's attached to this wheel, and wheel is connected to this cable. By rotating this shaft, which is connected to motor, this wheel is rotating, and of course the cable is stretched. If we look at the small part of this cable, we can draw it schematically as shown here. Because the cable is under stretch, so we will have a tensile force acting normal to this area. Remember, this area is the cross-sectional area when unloaded. Therefore, the tensile stress can be defined as F divided by A0. If we look at this part of the shaft, of course, we will see a torque or momentum that is applied in the shaft. If we take free body diagram of a small part of that, we have a momentum here, and we have another moment in opposite direction. If we look at a small chunk, a cube of this part, then we can see shear forces acting in this direction due to the load, the moment at this part, and the other moment at the other side of the cube. And we will have these moments in order to remain in the static situation, so that we have these acting forces on the cube. If the value of, or the cross-sectional area when unloaded, is equal to A0, then the shear can be defined as shear force divided by A0, and it's shown schematically like here. Note that the force is equal to the moment divided by the radius of this shaft, so we can write it down M divided by AC. A is A0 as the cross-sectional area, and R is the radius of the shaft. The other common state of stress forms when the whole material or the body is under compression. If you look at this cross-section A0, which is under weight of this stone, so this cross-section is under compression loading. The same thing is happening on this bar. The way of this rod here is applying pressure to the rod or to the profile here, so we can write compression stress is equal to the compression force divided by force before loading. As a convention, we agree that the value of sigma is smaller than 0. The other state is when the material is under two normal stresses as shown here in this pressurized tank when the wall of the tank is under two pressure. One of them is along tangential direction and the other one is along the direction or axis of the tank. The other common state is when the material or the body is under equal value of stresses in all direction, compressed stress in all direction. This is called hydrostatic compression, and an example is a fish underwater. The other term that is needed to be defined in when dealing with the mechanical properties of material is engineering strain. When material is under tensile load, of course we have increase in its length, so the change in the length divided by the initial length is called tensile strength. It is, of course, because this is in meter or centimeter, and the same for here for the dimension for the size of the bar, so stress is always dimensionless. For the lateral strain, of course, we have shrink in the lateral part, therefore we can write down the value of a stress equal to amount of change or shrink in the lateral part divided by initial width. Of course, because these two have negative marks, in order to make it positive we add a negative sign here. The other term is shear strain, and it's defined when a material is under shear. It is defined as you can see here, and it's denoted by gamma, which is equal to change in the value of x, or simply displacement of this point along x-axis divided by y-axis. And it's clear that this term divided by y is equal to tangent of theta. And theta is the angle showing the shear of the material. To find tensile compression properties, stress strain curve of material, tensile test machine is used. This is a typical tensile test. As you can see, the specimen is inserted here, and then this screw is rotating, and what's happening, this head is fixed, and by this screw going from top view going clockwise, then what's happening, the crosshead, this crosshead is going downwards. Therefore we have tensile stress or tensile load applying on them on this bar, and then it results in tensile stress. The displacement can be measured using this extensometer as shown. The extensometer measures the displacement of this part, which is supposed to be the thinner part, or the part of the material that has the smallest value of cross section, so it has the highest value of displacement. Finding displacement divided by the initial value of the gauge length here, the length of the tested area, it gives us strain. Finding the value of load from load cell and then divided by the initial cross section provides the value of stress. Here a typical tensile specimen which has a rounded cross section is shown here. To perform tensile testing, one can use ASTM, American Standard of Testing in Materials, or DIN, which is for German standard, and also ISO, which is International Standard Organization. And now let's go to problem A2. It actually talks about the value of normal and shear stresses along a certain angle of theta, which is defined by equations 8.4a and 8.4b. If you look at page page 214, equation 8.4a and 8.4b, where stresses along normal or along the direction of a plane which has angle of theta, we can find these values in terms of sigma, which is the normal stress, using this formula. Now we want to do equation problem A2. It asks us to make a plot on which is presented the orientation parameters of these expressions. So we want to make actually a plot that has this expression, cosine squared theta and sine theta cosine theta. To do so, we can use different online websites. One of them is Desmos, as you can see here. I just write down cos x to the power of 2. So this is actually showing the change of sigma prime at different angles. And this set the x-axis to be in radian or in the degree. Now I'm adding the second one, which is actually sigma. Assume a sigma has a certain value, and then sine theta, so sine x times sine cos x. For the value of star multiplication, I have to use this sign here. So now you can see the change, or we can compare the change in the value of sigma prime and tau prime from equation 8.4a and 8.4b. Using these curves, I can zoom in, and we can see the changes from almost minus 3 radian to plus 3 radian. The first question is from this plot, at what angle? So from here now, we want to see at what angle of inclination is the normal stress and maximum. The first one is showing the normal stress, the red curve, and you see the maximum value is happening here, and here this one is angle actually where the second part is ask us at what inclination angle is the shear stress maximum. Now we can see at this angle and this angle you can find their equivalent value of say for example this pi over 4 minus 3 pi over 4, so 45 degree here. If we plot the value of stress versus strain, then we note that the angle that is happening in the linear elastic part, the angle which is defined as stress divided by strain, this value is called modulus of elasticity, or Young's modulus. The relation between sigma and epsilon is termed as Hooke's law, as you can see here. Know that this material is under tension. By removing the load, it goes back to its initial value, and if it's under compression, it goes in this direction. And again, removing load, it should go back to its original position. The other term that is defined in the mechanical properties of material is Poisson ratio, which is denoted by nu, and it's defined as longitudinal value of stress lateral value of stress divided by the value of stress. And because this one is having a negative value, so we add a negative so that we end up with a positive value for Poisson ratio. Poisson ratio for metals are approximately around 0.33, and the rest are also depicted here. The value of Young's modulus, as we defined here, the unit is in Pascal or PSI, depending on a metric system or British system if we use. And from here you can figure out that the unit for Poisson ratio is there is no unit for Poisson ratio, and it's dimensionless. For Poisson ratio above 0.5, of course, we have density increases, and for this one we have density decreases. So this is a good question to ask in the class. Why? So I just put a Y mark here. When talking about elastic modulus or Young's modulus, bear in mind that this parameter depends on bond strength of metals. So if we have a stronger bond, we expect that the value of E is higher. Because of that, if we look at the table, this table showing the value of Young's modulus at different groups of materials, you see, for example, in metals, the ones that have higher or stronger bonds show higher value of Young's modulus. Diamond that has the strongest bond, covalent bond between carbon atoms, its value of E is very high, and it's the highest among all materials. Graphite that has a very low value of bond between the planes, van der Waals bond between the planes, shows a low value of E, and you can see in wood perpendicular to the grain size, and in some of the polyester we even see lower value of Young's modulus. In composite, if we talk about directions along fiber, we see higher value of E, and if we look at direction perpendicular to the fiber, because only matrix is withstanding the load, we see lower value of E. Here composite data is based on reinforced epoxy with 60% volume of carbon fibers or aramid or glass fibers. So the percent of fiber is also important in determining the mechanical properties. Here are some other useful relations that are valid in elastic region. The first one is what is shear modulus, similar to Young's modulus or elastic modulus. It relates shear stress to shear strain, and it's denoted here by G, so it's the slope of shear stress versus shear and strain. The other parameter is bulk modulus, which is defined by this relation and is denoted by K here. Bulk modulus can be determined by a pressure test shown here. How to relate Young's modulus to shear modulus and Young's modulus to bulk modulus, and determine and calculate it by knowing the value of E and Poisson ratio are shown in these two relations. The other useful elastic relation is when a material is under simple tension test due to force F, we have displacement of delta. We can relate the value of delta to the load, initial value of length, and cross-sectional area using this relation. It's actually resulted from Hooke's law. For lateral displacement, we can use the same relation and with the help of definition of Poisson ratio, we can derive this relation for the lateral displacement. For torsion, when the material is under torsion or is under bending, as you can see here, the angle of twist, which is shown by alpha, and it's measured from this one in the original position if it's 0, and then we rotate this one, this angle is angle of twist. The angle of twist is related to the initial length, to the radius of the bar, and shear modulus. As I previously stated, many of stress-strain behavior curve can be found using simple tension test. In this material, when we apply axial load, we see stretch in the bonds, so we will see increase in the length, increase in the value of stress, linearly with the value of strain for metals specifically. By continuing load, it starts to deform plastically. We already talked about plastic deformation, but here we have elastic plus plastic at larger stresses. And if we remove the load, it doesn't go back to its original process, but it goes back to a position, and the path is parallel to the elastic line here. This point is showing the permanent or plastic deformation after load is removed. The value from here to here, as I show it here, this value is equal to the value of elastic strain which has been recovered. This is good for the end of section 16, and we continue with mechanical properties. We will talk about yield strength, tensile strength. We will also compare materials with regard to their compression behavior in the next session. Thank you.